Hello students, in this video we'll show the set of rational numbers is countable. So our proposition is that Q is a countable set. To do this, we'll look at the set Hn of the set of all P over Q, such that P over Q is in lowest form, and Q not zero, of course. And then also that the absolute value of P plus Q is equal to N. And so N here is called the height of the natural number, so N is called the height. And so look at some of these examples of sets. So if we look, for example, at H1, the set of height 1, that would just be the set of 0 over 1, or the set 0. If we look at H2, the numbers have to add up to 2, so I can have a 1 over 1 or a negative 1 over 1. If I look at the set H3, what will H3 be? H3 is going to be, I can have a 1 over 2, a negative 1 over 2, a 2 over 1, or a negative 2 over 1. And we can continue on in this fashion. So it turns out that every rational number is mapped in one of these Hn. So note that each Hn is finite. Each Hn is finite. And every element of Q is in exactly one of these sets Hn. And so this is a countable union of finite things. So it's a countable union of, in some sense, countable things. So I have a countable union of finite sets is countable. There's an alternate proof that Campbell gave in the American Mathematical Monthly some years ago, which is a it's a nice sort of beautiful proof. There's also a way, there's another approach. And this approach is due to Campbell. And what this approach says is to do the following. You take a positive fraction, so you look at Q plus over here. And what we can do is we can write it as, for example, it would look something like this. It might look like A, in decimal representation, A1, A2 over B1, B2. And so what you do in this procedure is you count every symbol as a term in a base 11 expansion. So for example, you would associate this, there's 5 terms over here. And so what we would do is we'd say this is really going to be A1, and then I have a total of 5 terms, so I'm going to say 11 to the 4th power plus A2, and then we're going to have a 11 to the 3rd power. And then I'm going to say plus capital X, and capital X represents the 10th digit in base 11. So this is the 10th digit in base 11. That will be times 11 squared, plus B1, 11 to the 1st power, plus B0, 11 to the 0th power. So in this way, what we can do is we can map every positive fraction to a base 11 expansion. So in this methodology, every positive fraction, so hence every positive fraction is mapped to unique number base 11. And since every natural number is represented as a unique number base 11, I have a one-to-one correspondence between the positive rational numbers and the natural numbers in this fashion. So that's Campbell's proof, Campbell's approach to showing that Q plus is countable. So either of these approaches works, and we know that Q is therefore and I can actually, since we know that Q plus is countable, I know that Q minus is countable by a symmetry argument, and I just have to tack on 0 and we get everything we want for free. And that shows that Q is a countable set. Thank you very much.